Hey, Algebra 2, here we are with 6.3, and in this lesson we get to talk about logarithms and logarithmic functions, or logs as so often we call them. We're going to be talking about the definition of them and evaluating these logarithms or logs, and we're going to be looking at some properties, use inverse properties of logarithmic and exponential functions. One of the first things you want to realize about these logarithms and how they kind of connect together with exponential functions, because they're in the same chapter with exponential functions, is that they are the inverses of exponential functions. So when we say something like b to the x power, well, the logarithm would be the inverse of that kind of function. So as we go through this, you'll begin to see how that is true. First, let's take a look at a little Garfield cartoon. See, throwing the ball, playing a little fetch with Odie. Fetch the ball, Odie. Waiting for him to come back, and Odie brings back a football. Where'd you get that? As the football team comes screaming down behind him. I love Garfield. All right, well, let's take a look at our logarithms here. So, logarithms, as you can see here, we're not necessarily, I got some pictures of some logarithms, some log with rhythm here. Some of these guys that are in cartoons, they do these often to kind of help us, have fun with logarithms and just the word, the way it kind of sounds. So we talk about this. You know that 2 squared equals 4, and 2 to the third power equals 8. So we know that. However, for what value of x does 2 to the x equal 6? And if we try to figure that out, well, you're not going to be able to really figure that out, what the x would equal. It's some decimal, somewhere between 4 and 8. So, or actually between 2 and 3, I should say. Between 2 and 3, because 6 is between 4 and 8. So as mathematicians define this value using a logarithm, where we write this, x equals log base 2 of 6. So the word log is just, there to show us that we're talking about a logarithm. So it doesn't really need to worry about so much the word log. We're just going to get familiar with just seeing that. When you see the word log in the function, then you know you're talking about a logarithm. So they're very clearly marked with the word log there. The definition of a logarithm can be generalized as the following here. And so you do have this. You want to highlight this part here, a logarithm of y with base b. So that's what a logarithm is here. So the logarithm y of base b is basically what we have in this part here. And here's what you want to write down for that there on page 166. You can write there where the core concept is, or you can write at the very top where it says this right here, logarithm of y with base b. That logarithms, they equal exponents. That's the number one thing you want to remember here from this lesson, is that logarithms equal exponents. And so as we go through this, you need to continue to keep that in mind. And you'll see that as we start to go through this part here. So we have this kind of definition. You want to write on your core concept right above this part here where it says log base b of y equals x if and only if b to the x equals y. So we talked about that already, that b to the x equals y is the exponent form. So that's an exponential. So we want to put exponent form right above that. So do that right there in your paper on 166. Put exponent form above this one. This is the log form. So these are equal to each other. They are the same kind of thing. This is just a log form of this exponential form. And so we can kind of go back and forth between these. So we can always change a logarithm into an exponential form, because logarithms always equal exponents. You want to write that right there kind of next to the core concept. Logarithms equal exponents, and highlight that, circle that or something. So here's another thing. This definition tells you that the equations log base b of y is equal to x, and so we talked about those two things. They're equivalent. They're equal to each other. So we say these are equal to each other. And what you want to write down, just maybe right underneath the core concept, is what I have here in red. It puts this a little bit easier, where we can use some letters that may stand for base and exponent and number. So in this form is our log form. So it's basically the same thing as this. Instead of using x and y, I'm using n for number and e for exponent. So log with base b to the number here equals an exponent. And it's the same thing as over here if we said base b to the exponent equals the number. So we can change our form. If we have a logarithm, we can change it into this form. We can take this base to that exponent, and it will equal this number right here. We could also go back this direction. If we have an exponential, we can put the word log here. This would be the base, this little number down here. The number would be next to that, and it will equal the exponent. As you can see here, logarithms equal exponents. This is our logarithm right here. Log base b of the number, n is the number, and it equals e. E is the exponent. That's what you got to continue to remember, that a logarithm, when you're trying to evaluate a logarithm, where we're trying to figure out is what is the exponent there for the base that will give us this number. That's why we can think of it in terms of this. So we're trying to solve for a logarithm or evaluate a logarithm. We're looking for the exponent that we would raise this base to equal this number. That's why we can always think of it in this term. This base to the exponent equals that number. Okay, so on page 167, there at the very bottom, we have 1 through 4 in the extra practice. We're going to rewrite the equations here that they give us in exponential form. You can see the word log, so you can see these are all in logarithm form because of the word log. We're going to change them now to exponential form. So we need to remember what each of these parts, there's 3 parts to this equation with the logarithm. You have your base part, which would be right here, so this is your base part, the 10 is the base. You have your number part, that's the 1000 number right there, so I'm just going to put a number sign there, that's our number. And we have our exponent part. The logarithm always equals the exponent, so 3 is the exponent. And so now what we can do is we can say, okay, the base to this exponent equals this number. That's how we can change this into it. So we're going to say 10 to the 3rd power, that's the base 10, to the exponent, 3 is the exponent, and it's going to equal the 1000. And there it is. Do the same thing on the next one. So our base is 5, the exponent's -2. So 5 to a -2 power, and it will equal this number part right here, this 1/25th number part. And there's now our exponential form. So logarithm form, and it's changed now to exponential form. Go ahead and stop the video for a second, or pause it, and just do the next two. Do number 3, number 4, change these from the log form into exponential form, and then start the video again and see if you got them right. Okay, so we're going to do these two here. Number 3, we're going to see 10 is the base, 0 is the exponent, so 10 to the 0 power will equal the number 1. And on number 4, we're going to see the base is 1/4, the exponent's -3, so 1/4 to a -3. Now I put that in parentheses because it was a fraction there. So 1/4 to a -3 power is equal to the number 64. And that's it. That's all there is to it, going from logarithm form to exponential form. Okay, if you just turn the page, at the top of the next page, 5 through 8, we're just going to go the opposite direction. We're going to now change it from exponential form into logarithmic form. So now we're going to write the word log here. That's the first thing we're going to do, is write the word log. So we have our base, our exponent, and our number. So we're going to start with the log word with the little base number. The base is 12. That's going to be the little number of the number 144. And so we got the log base 12 of the 144, and it's going to equal the exponent. So it equals 2. So the logarithm always equals the exponent. And the number 6 one here, we're going to see the base is 20, so we're going to say log base 20 of this number here, the 1/20th. So log base 20 of 1/20th, it will equal the exponent of -1. So it equals -1. The logarithm is going to equal the exponent. So go ahead and do the same thing. Go ahead and pause the video. Do 7 and 8. Try that. Change it from the exponent form into logarithmic form. Okay, so our base here will be 216. The number is 6. So log base 216 of 6 is equal to the exponent of the 1/3. And number 8, we have a log base b of 1. The number is 1 here. So log base b of 1, this is how we read this, log base, or base 4, I should say, log base 4 of this number 1 is equal to the exponent of 0. So equals 0 on that one. Okay, so this can always go back and forth. You can go from log form to exponential form to log form anytime we want to. Okay, so on 9 through 12, here we're going to evaluate the logarithm. And so we want to actually figure out what is the exponent here. So what exponent do we need to raise this base number to give us this number part here? That's what we're trying to find the exponent. So the logarithms will equal the exponents. And if we want to actually make the equation out of it, we can put equals x because we're looking for an exponent. So if we want to do that, we can do that to every single one of these. Sometimes I do that just to see it where I see my base, my number, x is my exponent. So I'm looking for the exponent here in this one. Now sometimes they put that x in other places. So sometimes they might give you the exponent number here and put the x down here, and you got to figure out what the base is. Or sometimes they might put the x here and you got to figure out what the number is if they give you a base number and an exponent number. So we still want to do the same thing, change the logarithm form from this form to exponential form. That will help us figure out what this x is going to be, what this exponent is going to be for these ones. So starting with number 9, we're going to see our 4 is our base, x is the exponent. So we're looking for the exponent here. So 4 to the x power is going to equal 64. So we want to think about, okay, what number do we need to raise 4 to give us 64? And we know, well, 4 times 4 is 16. And then 16 times 4 again, that's going to be 64. So 3 4s multiplied together will give us 64. So x would have to be 3. So the exponent 4 to the 3rd power equals 64. So we just kind of think about it in our head, or look at our charts that we have in class, and you can do that. Number 10, we have 1/8 to the x power. So 1/8 to an x power. So we're looking for the exponent again. Is going to equal 1? So we need to realize that, okay, if it's going to equal 1, anything to the 0 power will always equal 1. So in this case, x would have to be 0 for it to be able to equal 1. So x is 0 on this one. Anything to the 0 power. So if it says equals 1, your x here, your exponent has to be 0. This one, we got 2 to the x is equal to this 1 over 32. So 2 to the x, your base to that exponent, we're looking for what exponent are we going to raise the 2 to give us a 1 over 32? Well, it's going from a whole number here, 2, to a fraction. So it looks like we're flipping it, or at least making it into a fraction. So if we think of this as 2 over 1, our exponent is going to have to be negative to be able to go from 2 to a 1 over 32. And you think, okay, how many times do we need to multiply 2 to get to 32? So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's 5 times. So x has to be a negative 5 here to be able to give us this 1 over 32. The negative sign, we'll flip it and make it 1 over 2 to the 5th, and 2 to the 5th is that 32. So our x here has to be negative 5. On this one, we have a 1/25th is our base, and x is the exponent, and it's going to equal a 1/5. So we're at a fraction. We're going to stay a fraction here, but we're going from some kind of a bigger number 25 down to a smaller number of 5. So how do we get from 25 down to 5? Well, if we think about the square root of 25 is 5, that will help us. So if we took the square root of this 1/25th, it will equal 1/5. So if we think about this, the square root of this 1/25th, it'll equal what we have here. So now what exponent would be this square root sign? Because remember, square root signs are fraction exponents. So the square root, the 2 would be the base, and there is no other exponent here, so 1 would be the numerator. So 2 would be the denominator, and 1 would be the numerator for our fraction exponent. So that's what it's going to be. This 1/25th would be raised to a 1/2 exponent. That's what would give us this 1/5. So our exponent has to be a 1/2. So x is 1/2 on this one. So if you're going from like a 25 down to a 5, think about square root, and now you got a fraction exponent. So you might have fraction answers here because of the rational exponents like we learned in chapter 5. All right, here's our little break for joke of the day. Where do you find a no-legged dog? Right where you left him. Might have to think about that for a second. Okay, so on the top and bottom of 166, if you go back to 166, we're going to take some notes in that section. So let's start with these always logs. This is down at the bottom of 166. You have a big section, blank section there for notes underneath that core concept. And you can write down always logs, and you want to put logarithm of 1. We kind of already saw this a little bit. that if we have a 1 here for the number part, if this number is 1, you want to write this down. Make sure you write logarithm 1, log base b of 1 equals 0 because b to the 0 power equals 1. So here's what we know. We know when this number is 1 right here, when your number part is 1, it'll always equal 0. So we saw that back on, which number was that? Number 10. So number 10 had that very same problem. It had a 1 right here in the number spot, and our answer was 0. That will always be true. If you have a number 1 here, it's 0, and the reason why is because anything to the 0 power does equal 1. Here's another one, logarithm of b with base b. So if your base and your number part are the exact same thing, it will always equal 1. It will always equal 1 because b to the first power is b. So if you raise anything to the first power, it'll just give you what you have already. So that's why if these two are the same number or whatever it is, it'll always equal 1. So those should be on the bottom down below your core concept on 166. Now if you go back to the top, we have two vocabulary to put in. First, common logarithm, and then natural logarithm. So these are two kind of special logarithms that we talk about. The common logarithm, what you want to write for that is it's a logarithm with base 10. So if it just says log, then it means log base 10. And so what you want to write down here for common logarithm, you want to write this down also next to that vocabulary. Log base 10 of x is the same thing as saying it log x. So if you just see log x, you know it means log base 10 of x. So base 10 is so common that a lot of times we don't even write the base. We just write log. And then the natural logarithm is a logarithm with base e. That's that 2.71 or 2.72 number. So we want to write this down next to the natural logarithm, that log base e of x is equal to ln x. So here's how we notate the natural logarithm. And it's kind of backwards. It looks like natural logarithm would be nl, and it's notated ln. So it's like log natural. But that's what it means. When you see this little ln, it just means it's a logarithm with base e. And these two are actually on the calculator. So you can see on this calculator on the computer, here's my log button, and up here is the ln button. So those are the natural log and the common log. So if I hit this log button here, that whatever I put in now is going to be the common log, log base 10 for that. If I hit the other one here, ln, that's going to be the natural log. So we're going to be talking about the natural log when I hit that button. So if we wanted to calculate these using the calculator, we can calculate for log base 10 and log base e. And those are the only ones that we have for the calculator. We don't have log base of anything else. We can calculate log of other bases if we, once we learn a property, and we'll learn that in another lesson, of how to calculate logs of different bases, even on the calculator. But if you just want to figure out, log base 10 of something or other, so let's say, log base 10 of 10, we'll look at this one right here. So if it says log base 10 of 10, it should say 1 for what we got here. So if I say 10 and then hit the log button, it equals 1. Log base 10 of 10 is 1. And the same should be true with the natural logarithm. If I say, natural logarithm of 1, it should be 0. So let's try that one. If I say 1 and the natural logarithm, it does equal 0 right there. Natural logarithm of 1 is equal to 0. So these always logs apply to these as well. Okay, staying on page 166, I'm going to have you write these down. If you want to number them 9, 10, 11, 12, that's fine. The numbers really don't matter because these are not in our extra practice. But just I wanted to get a little bit of a practice on these because they're not there in the extra practice in the evaluation. So it's to evaluate the logarithm. If necessary, use a calculator. Round your answer to 3 decimal places. And that's usually the case with all logarithms. They're going to round it to 3 decimal places if it's going to be a decimal. So first of all, 9, we would want to see that that's going to be 2 to what power? We're looking for the exponent here. So 2 to what power will equal 32? So basically you can think of it in this way. Oops, lost that there. So 2 to the x power equals 32. So what do we need to raise the 2 to give us 32? We already talked about that. That was 5. So we know this one is going to be 5 here. So that one's 5 for this one. So our exponent will equal 5 for this one. The logarithm will equal 5. On this next one, 27 to what power will equal 3? So we're thinking about this. 27 to what power equals 3? Now we're going from a bigger number to a smaller number here, from 27 to a 3. So in order to do that, we got to, think about some probably kind of root, kind of when we did 25 down to 5. That was a square root. Well, 27 could be the cube root of 27 would actually be 3. So if you remember that, the cube root of 27 is 3, and now we can think about, well, what's the cube root as a exponent? Well, the denominator would be 3, the numerator would be 1. So 1/3 is the exponent for that one. Oops. I'm going to do that. There we go, 1/3. And now for these two, 11 and 12, log 12, remember log 12, remember write these down. You're writing these down. So you're writing log 12 down on page 166. That would be the common log. So we want to grab our calculator again. And here we can evaluate this one for log 12. On this one I got to hit the log or the 12 first and then hit the log button. Sometimes I got to hit log button then the 12. Just depends on the calculator you're using. So log 12 and then the log button would give me this decimal, 1.079. So that's 3 decimal places. So there it is, 1.079. And then for this one it says natural log of 0.75. And if you hit the log button instead of the natural log button, you would get the wrong number. It's not going to be the same thing. This is log base e, and this is log base 10. So that would not give you the same thing. So we got to make sure we're going to hit the ln button for this one. I'm going to put 0.75 in first, hit ln button, and that will give me my answer, negative 0.2876, so maybe 2.88. Let's see what it says here. Yeah, negative 2.88. That's what's going to give us that. So just use the calculator when they want you to evaluate the common log, when it just says log of some number, and the natural log. Because obviously we're not going to figure this one out. It's a decimal for the exponent. This 1.079 would actually be the exponent for this. 10 to this exponent would give us 12. We could even check that on our calculator. We could say 10 to this exponent, and it should be approximately 12. I know we're writing a lot of stuff on page 166, so back at the bottom of page 166, probably closer to the bottom, write down inverse properties. So kind of title this little part here, inverse properties, and then write down what I put in parentheses here. You don't have to put it in parentheses, but I just did that so you can see what you need to write down. So write this part down here, and really specifically we need to highlight this thing here. So we see the b to the x here. That's already kind of an exponential. And this is the part that we want to realize, that we got log base b to this b to the x. And over here we see log base b of x, and here's the part where we need to realize this is b here in front of it. So inverse properties is basically saying if I did this, if I have b to the x power, and I want to figure out what x is, what I could do to that is I could kind of give it a log of its same base. So base b, I can give it log base b. And so this log base b with that base b here would actually be the opposite or the inverse of each other, and they would cancel each other out. They would undo each other, leaving us just with the x. That's how we can kind of free the x if we had something here like that. So if we want to solve an equation or figure out what the exponent is on something, then we can do this. We can kind of zap it with a log of its same base, and that would cancel that out, and it would free the x. Or if we have a logarithm like this and we want to solve for x, we could do the same kind of thing. We can zap it with the base. So if it's base b here, we zap it with b here. These would cancel each other out, and it would also free the x. They undo each other. Okay, so here we got to realize the exponential functions and the logarithmic functions, they undo each other. And you probably want to write that down here because they're inverses of each other. We talked about that at the beginning, that exponentials and logarithmic functions are inverses of each other. The graphs are inverses of each other. The functions on the equations here are inverses of each other. They undo each other. Okay, so for number 13 and 14, we're going to use those inverse properties here to simplify the expression. On 13, we can see 13, this base here. So we have this log base 13 of 6, and they're kind of giving it a base of 13. So that's the same kind of inverse one as this one, where it's got b here, log base b of x. These two cancel each other out, it frees it, and now we have x. So if we want to simplify this, we could free out this 6 by canceling 13 with log base 13, and now it's just going to equal 6. So what's left would be the 6. So there's your simplified. So this would simplify just to 6. Here we need to remember that this is basically log base e. ln, the natural log, is log base e. So we have a situation like this. We have log base b of b to the x, because we have the log base e of e to some power here. And so to simplify this, we can see it like this and cancel out the log base e with base e. And now this x to the third power will be freed, and that's what we would end up having, just x to the third power as the expression. So these undo each other, and now it just frees the x to the third. That's what would be simplified. So using those properties real quick. Okay, so in 15 and 16 it says find the inverse of the function. So we were going to use those inverse properties again to help us find the inverse of this function. So on 15 and 16, what we need to remember here, whenever it says find the inverse of a function, we have to remember switch and solve. So there's two things to do here: switch the x and the y, and then solve for y. So remember, switch and solve. So number one, you want to write down this here to remind yourself: switch x and y. And then number two, solve for y. Okay, so those are the two things to do. We're going to first switch the x and the y in this problem. And if it doesn't have a y, if it has an f of x or something like that, you first change it to y. But we already have the y here. So I switch the x and the y, and now it'll look like this, where it's going to say x equals 15y plus the 10. And then to solve for the y, we first are going to move the 10 to the other side. We're going to subtract 10, get this part by itself. So we first subtract the 10 from both sides. Now I have x minus 10 is equal to 15y. Now to undo and get y by itself, we're going to use that inverse property. So I have a 15 as my base. I need to zap both sides here. Whatever you do to one side, we're going to do the same to the other. So we're going to zap both sides with a log base 15. So that's what we're doing here. We're going to zap it with log base 15. That way that log base 15 and this 15 can cancel because of that inverse property. They undo each other. That would free this y now. And over here I'll have log base 15 to this exponent. X minus 10 would be the exponent. And that would be what I have for my answer. Actually, so not for the exponent, it would be the number part. So we log base 15 of x minus 10 is equal to y. Y would be the exponent in this case, if I change it to exponential form, which is what it was here. All right, so basically we're actually, another way you can do this is actually, you have an exponential form here, we can change it to logarithm form by writing the log base 15. This is the number part here, y is the exponent. So there's another way you can do this, same thing. So you can use it with the property where you zap both sides with log 15 to get rid of the 15, or you could just change it from exponential form to logarithm form, and there's your answer. Here's a natural logarithm. ln's the natural logarithm. First we're going to switch the x and the y. So we'll do that first. And whenever I see ln, I like to change it to log base e. I like to actually see that e there. So I'm going to do that, log e here. And the first thing we'll do to get y by itself is add the 8 to both sides. So get the 8 on the other side. So it's going to be x plus 8 now on this side is equal to log base e of 2y. And now to get this, kind of 2y part, I need to get rid of my log base e. So I need to kind of zap this one with e on both sides. I could also change its form, so we'll talk about that too. But I can get rid of log base e if I give it a base e. So if I do that, basically, put a base e for both of these. So now this is base e and x plus 8, that's the exponent. That's what I was thinking about over there. So this is now the exponent, e to this exponent here. E to this will cancel out the log base e. So e and log base e cancel out, leaving us with the 2y. So now 2y is equal to the e to this x plus 8 exponent. And now to get rid of the 2, we just got to either divide by 2, so we could do that, divide both sides by 2, or multiply by the reciprocal. That's what I chose to do here. Multiply this by the reciprocal. So that cancels the 2's out. And now it just is 1/2 times e to this exponent of x plus 8. And that can be what our answer is right there. So y equals 1/2 e to the x plus 8 exponent. So instead of zapping both sides with e here, I could have changed it from basically log form to exponential form. So I say here's my base, this is the exponent, so base to the exponent equals the number part, and I could have done that. So again, you can always change from one form to the other form, so I could have done it that way. So doing these undoing properties here with the inverse is the same idea pretty much as going from one form to the other form, because remember, exponential and logarithmic are always inverses of each other, so when you go from one form to the other form, you got the inverse. Okay, so the last thing to talk about here in this section is the graphs for the logarithmic functions. Parent graphs of logarithmic functions are in this core concept. And remember, we just talked about that the logarithms are the inverses of exponentials, so that's why you see the graph in blue here as the exponential function. This would be exponential growth. Here in red is the logarithmic function here, and it's going over, it's being a reflection over this line, this diagonal line, which is the y equals x line. And that's what we're seeing here, that reflection, it's a reflection over that line, because we talked about that when we did inverse functions, that the inverse function is always going to have a reflection over this line. You can see that it's always going to be exactly the same distance away from that line of reflection there. Another thing we might want to notice here is we had two different ones. So this is one for growth. So when b is greater than 1, it's growth like this. And this is what our function will look like. It's going to be kind of a waterfall looking function. And this one's going to be for decay when b is between 0 and 1. So when this number is less than 1, here's our decaying function. And then the red one here, this would be the logarithm. The reverse of that, the inverse of that, would not be the same as this. It's going to be, this kind of reflected over this y equals x line. So it's going to be kind of more, like this way here. But one thing that's true about the logarithmic functions, and you want to highlight this in this core concept right there on page 167, is that the y-axis is the vertical asymptote of the graph. So we talked about with the exponentials, these blue ones, the x-axis, you had a horizontal asymptote. But now with the logarithms, it's the other way around. It's going to be a vertical asymptote, a line, this is the line you cannot cross. It's not going to cross or touch this y-axis line right there on this one. Another thing that is also reversed, we talked about the domain and range of these, where the domain is going to be all real numbers and the range is going to be an inequality. Now it's reversed. The domain is now the inequality. Range is going to be all real numbers. So highlight that range is all real numbers for all logarithms, but the domain is going to be some inequality here. In this case, it's going to be x is greater than 0 because of where it is on the y-axis. Your asymptote's the y-axis, which is when x is 0, so it's going to be greater than 0. You're going to find this on the x-axis, just greater than 0. It's not to the left at all. It's only on the right of the y-axis, which would be greater than 0. Okay, so our last two problems, 17 and 18, want us to graph this function, determine the asymptote of the function. So we can kind of determine the asymptote of the function right away. Just by looking at the function, we can see it. It is always going to be the h number of the function. The h number is always the number in where x is. So you can see in the parenthesis here, this we have x plus 1. It's always the opposite of what we think, though. So our asymptote is going to be negative 1. So the h number here on this one is going to be negative 1. So that's where the asymptote is going to be. Where x equals negative 1, it's going to be a vertical line going through right there where x equals negative 1. That's going to be the asymptote of the line that we cannot cross. Alright, so if we want to graph this, we can start to change this into exponential form. So we can do that maybe first. So if I do that, I'm going to say, okay, my base is 2, my exponent's y, so 2 to the y power is equal to this number part of x plus 1. And since y is the exponent, and we are going to plug some numbers in for our table of values, the numbers that we want to plug in is really going to be the opposite of what we've done in the past, because remember, this is the inverse of an exponential. And when we were graphing the exponential functions, we put numbers in for the x, which was the exponent spot. Well, now the y is in the exponent spot. So we're going to put numbers in for the y, for this logarithm function, and then figure out what the x equals from that. So I'm going to start with the number negative 1. If I put negative 1 in for y right here, 2 to the negative 1 power is going to give me a 1/2, because it's going to flip it upside down. It's going to flip what I have here of 2. So it's just going to be a 1/2 is equal to x plus 1, and then we just got to subtract 1 from both sides. And when we do that, if I take 1 away from, or I should say I take a half away from -1, it's going to leave me with a -1/2. So we're going to get -1/2. So that's going to be on our graph. We can put that down. We can go to -1 and then 1/2 up, or I should say 1/2 and then -1. We're going to be down here. So you go halfway to the left and 1 box down. There you are. The next one I'm going to choose is 0. If I put in 0, anything to the 0 power we know is going to be 1. So 2 to the 0 is 1, and then we just got to subtract 1 from both sides. So 1 minus 1 is going to give me 0. So 0, 0 is another point on this graph. We're going to go right through the origin. I'm going to pick another point of 1. So 2 to the first is 2. When I subtract 1 from both sides again, we're going to see 2 minus 1, which would be 1. So 1, 1 is also another point on this graph. I'll be putting it right there. And then I'm also going to pick 2. So I put 2 in. 2 squared is 4. And so now I'll see 4 equals x plus 1. So 4 equals x plus 1. Subtract 1 from both sides. 4 minus 1 is going to give me 3 for this one. So 3 is the x. So 3, 2 is another clear point. So 3 and then up 2. And that's enough points probably to get it. We can go to another point, but that's probably enough to be able to put down. I'm going to put those 4 points down. I drew kind of a green dashed line here, right where the -1 was, so I know not to cross that. And I'm going to start to connect my dots, and I'm going to just kind of keep getting closer to that green dashed line. That's the asymptote line, and just not touch it. And it's going to go out this way and put arrows on the ends. Yeah, on this one, the first thing we're seeing here, what would the h number be? Well, it's not going to be -4 or even +4. It has nothing to do with 4 because it is where the x is. If it was going to be this 4, this would have a parenthesis here like this one did. So there's no parenthesis. That means there's nothing there with x. X, it'd be like x plus 0 in a parenthesis. So your h number on this one is actually 0. So where is it going to be 0? It's going to be right on the y-axis then on this one. Our y-axis is going to be our vertical asymptote on this one. So the first thing we want to do is get this logarithm by itself. We want to move this over. We want to add 4 to both sides. So we get the logarithm by itself. So here's what I'm doing. I'm adding 4 to both sides for this. So y plus 4 is equal to now the log of 1/2, log base 1/2 of x. And then from this point, we now can change this from the logarithm form to an exponential form. And I think that sometimes helps us get it a little bit easier if we change it from the log form to the exponential form as we're trying to plug in numbers. So to do that, we're going to see base is 1/2. The exponent is y plus 4. So 1/2 is the base, the exponent is y plus 4, and it's going to equal x. So as we look at a table of values, we're going to be putting, again, numbers in for y, because that's where the exponent is. And we want to be strategic about these numbers. I'm not necessarily going to put in 0 or 1, because we have a 1/2 as its base. So I'm going to try to be strategic about numbers that would work here that might be best for the 1/2. So I'm going to start with -6. And the reason why I'm starting with -6, negative will flip this upside down and give me a whole number. Right? So the negative is going to do that. So it's going to be -6 plus 4 is going to give me -2. So now I have a 1/2 to a -2 power. If I flip it, that's going to be 2 squared then, giving me 4. So 4 is going to be my number of that one. And next number I'm going to keep doing with just negatives. Just going to stay in the negative region here on the y. So that way I can flip this 1/2 to 2 and then just raise it to an exponent. So -5 here would actually give me a -1 exponent. So that's just going to be 2 to the first, which is just 2. And then -4, I'll just keep doing that. That's going to give me a 0 exponent. Anything to the 0 power is going to give me 1. So I'm at 1 on that one. -3 will be our next one. So that's going to give me to the first power. So anything to the first power is going to be what the base is. So this is just going to be a 1/2. So a 1/2 on that one. And if I did -2, now it's going to be a -2 or a +2 exponent. So that would be a 1/2 times 1/2 would be a 1/4. And there we go. So let's go ahead and plot these points now and look at our graph. So our graph, there's our asymptote. I did it with a green dashed line again, just right over the y-axis. And I started plotting these points. So I got 4, come over 4, and then down to -6, come to 2, down to -5, 1 down to negative, down to negative 4 when I go to 1. If I go to a half right here, I'm going to be going down to negative 3. And if I go to 1/4, I'm going to come down to negative 2. And so it's just going to kind of do this thing. If you start from here, you're going to get closer and closer to this y-axis and just keep zooming up, but just don't cross it. Try not to touch it. I mean, if you touch it, it's, okay, but you're not really supposed to. And then just put an arrow on both ends, and you've got it and you're done. You can always check these graphs as well with the Desmos calculator. You can type this in and make sure that your graph is correct. Alright, so that does conclude 6.3's lesson as we introduce the logarithms. We'll get into more things with logarithms, with properties and solving equations here in a little bit on the next couple lessons. So I will see you in class.